Welcome. So I've been building distributed systems for quite a while now. I've been in software for 2 decades now, even though I don't always like to admit it, but anyway, and building distributed systems with messaging and eventing for at least a decade. And to summarize it, it's hard, okay? It's a lot of fun, but it's very hard to build these types of systems and to put them into production and maintain them. And over the years, I've had so many heated discussions with all of my colleagues about so many different concerns, from how many services do we need to build these systems, and what are the service boundaries going to look like, and no, they should go here, and that should go there, and it becomes like very difficult discussions. And we discuss things like, okay, what type of communication do we use? Is it going to be synchronous or asynchronous, and where do we use its communication style? But also, should we then use commands or events? And this also leads to many discussions. Who was in my talk yesterday? Well, okay, welcome back. But then you will remember some of those things from yesterday's talks. Also, like, how does the workflow look like, and which coordination mechanism should we be using? And we spend a huge amount of energy thinking about all of these concerns, and what I've seen over the years is that there was always a blind spot. And that's change. Because that's the inevitable, right? Whether we want it or not, how much we take care of the design or not, things are going to change, either because we get better insights on how the domain actually works, or because the business keeps evolving. And it can be frustrating, but it's actually a good thing. It means we still have a job to do, right? But to successfully prepare our systems in terms of, evolving those systems and versioning them without breaking everything, we need to do a couple of things from the beginning. And one of those things is also thinking more deeply about how do we design our events so that we can make them easier to change later. So let's consider an example. Let's say that we have a credit card, and it's a very simple one, okay? I get to spend money on it, and whatever I've spent at the end of the month, I'm going to have to repay with a linked debit account, okay? So no sort of longer types of loans or longer payback type of periods. We don't do that. Very simple. And we have this credit card transaction service that takes care of all of those operations. So when we start to think about what can happen on a credit card, well, then you could quickly conclude that, well, either you deduct from the card, you spend money, or I change my mind about the pair of shoes that I bought and I send them back, and then money comes back onto that card because there was a refund. So we could say, okay, single event, right? We have a credit transaction made event, and that has an operation type to indicate whether money went off or on, so debit or credit. And this looks good when we start off because it's simple and it works for all of these cases, but this starts to break apart pretty quickly when things start changing. Because our stakeholders come back and they're like, you know what, we would like the ability to reserve funds on the card. So when people go to hotels and you check in, they ask to block a certain amount on your card just in case you want to run out without really paying the bill, right? Mitigation strategies. But at that point, we could look at that event and say, you know what, we could just introduce this additional operation type called reserve funds. And then we also will add this reserved until so we know how long we need to block that amount. But the impact on our consumers is massive. Because if our consumers thought, well, the operation type can only be debit or credit, now you've introduced a new thing and that could break. And if they have a defensive programming model, then at least they'll ignore it. But in order to also start consuming that information, they need to start to understand this new operation type and also understand which are the additional fields that are linked to that thing. So you get a lot of beautiful if-elses that nobody really likes, right? So this is not really great, but it can get much worse because the bank comes in and they're like, you know what? Credit cards were made to spend money in a store or on a public website or whatever it is, but they're not really made to use at an ATM and deduct money, and we want to really discourage that. So we're going to make people pay for it, right? And then we look at our payload again, and we're like, okay, you know what? We could just, we still have that debit operation. You're still withdrawing money. It's just this additional cost that is now introduced. So we add this additional field. And it's fine, right? I mean, we can make this required, and the default value will be 0. It's all good. And then we can still differentiate which amount they actually withdrew and what exactly the cost of that thing was. But then we face this issue where people start to withdraw money in foreign countries. That's fine. I mean, we were already prepared for that because we had a currency as part of our event payload. But what about the cost? Is that now in euro? Is it in US dollars? So the obvious choice could be to add even an additional field and then keep polluting this event payload. Or worse, we could tell our consumers, you know what, you can just assume that that's always going to be euro. That's never going to change. Of course it will. And then what you've done is you've basically introduced what's called functional coupling. Because now your consumers need to understand something that they shouldn't be caring about. That cost is expressed in euros, which they are unaware of and should be unaware of because that thing can change. And it's not necessarily something that they care about. So we looked at this and we're like, yeah, this is not really great. You know what? Actually, that cost should be another instance of this credit card transaction made event, and then the operation type should be cost, and then we have a currency and everything is solved. So you know what? We're just going to remove this cost from the payload and everything's going to be fine, right? YOLO! But then the question is, how does this affect your consumers? Because now you've removed a required field. Well, it's very simple. This breaks your consumers, and it turns into what we call poison messages, because your consumers are now receiving messages that they expect certain things to be in there, which is not in there, so they are just not able to even deserialize that anymore. It's like, well, I don't know what this is, right? So even though we can retry this as many times as we want, it will basically end up in an error queue or a dead letter queue, whatever it is. And then from a producer perspective, you could say, oh, come on, it's not that bad. You can just upgrade to the latest version of that data contract, and everything will be fine. And your consumers are like, excuse me? What do you mean everything is going to be fine? We have so many in-flight messages on our queues and our topics. How are we supposed to deal with multiple events that have one type and the others have another type? But also, what if there are delayed messages that have been scheduled that don't even appear yet? How am I supposed to deal with those? And then another consumer comes along and says, you know what? We actually found a bug in our system, and we have a bunch of these messages in our error queue. We're trying to fix the error, and we're going to deploy, and then I would like to go back to my error queue and retry all of those messages. But if you change the data contract, then how am I supposed to deal with both of those versions? And most importantly, really? I mean, we have our own deadlines. You can't just impose change on us like this, right? You are removing our autonomy. You're stealing it. So then you get teams that escalate to their product owners and their managers, and then the managers start fighting with each other, and we look at who has, I don't know, more leverage within the organization. And worst case scenario, the producer has to go back and undo all of those changes. And then in that case, the producer loses autonomy because they can't evolve things according to the rate that they're looking at. So what do? We can basically avoid many of these problems by better designing our events to begin with. One of the things that I try to do is to focus on more granular and more business meaningful events. Because I talked about debit and credit. What does that even mean? Maybe it makes sense within the context of a credit card. But what does that mean like outside of that service boundary or bounded context? It might mean nothing. Or worse, it might mean something completely different. That's one of the reasons we do DDD, right? But one of the ways to mitigate that is to really think about your events from an outside perspective. What just happened? Well, what just happened is that a payment was made with that card. And if money came back, then a refund was issued. And maybe there were funds blocked on that card. And finally, it could be that there were costs incurred in one of those transactions. And then from the outside perspective, you get much more meaningful events. And that allows each event type to basically only carry those attributes that actually would have value within that context. And you get rid of these ugly if-elses in the consuming code. So I like to focus on granular but business meaningful events. And that means that I will have a single event type for anything that has a meaning. So everything that says type is already tricky. Whenever you see the idea of a type, then you should be asking yourself, do I have multiple events in disguise here? For me, the meaning of an event type must remain stable over time. Because that allows, things will change anyway, right? Even within the meaning of a single event type. But at least you are managing that change if you keep it also to a single meaning. This also allows your event types to start evolving independently without causing issues in consumers that may only care about other operation types. Your consumers then also get a lot more flexibility by only subscribing to the things that they actually care about, and this keeps their own code much more concise and much more simple. No if-elses. Yes? But sometimes this is also not ideal, and your consumers really don't want all of those events because there are so many of them, and they're so granular, and it's a lot of noise for them, and what they really want is just an overview of what happened. And the way that this is usually solved is that you get consumers that will then start to subscribe to all of these events and then make something, a summary of that information that then becomes meaningful to them. And they start to aggregate that information. So in our example, let's say that I just want to understand at the end of the month what money was spent. Like, what do I need to deduct from that person's linked debit card? That's another service. And that's all I want to know. Well, what would happen now is that I have to subscribe to payment made, to refund issued, and to cost incurred to be able to understand that. And if there are new event types added that affect the balance, then I need to subscribe to those as well. Or if something is changed, then I would have to unsubscribe. For example, if all of the costs incurred are only basically deducted on once a year instead of every month. So you become exposed again to that functional coupling, because now your consumers need to understand all of the events that would have an impact on that balance. And this is why it's so important that we differentiate public events from private events. And I know there are many different terms for this that are thrown around everywhere. There's the concept of domain events and integration events and events on the inside and events on the outside and external and internal. You know what, I call them public and private because it just helps me to look at things from the perspective of what I really care about most. My service boundary, my bounded context. What is internal to it? What is external to it? And that makes it easy for me to reason about it, but whatever you feel comfortable with. And this is where we can then introduce a summary event to start to solve this problem. Because that can then be a public event that is accessible by all of the other boundaries that participate in our system, and that could be a card period closed event. Okay, so for this period of time, on this specific card, you spent, 500 and something euros. And that's all I really wanted to know. And we can handle that within the service boundary of this credit card operation service by subscribing to the payment made and the refund issues and the cost incurred events, and then aggregating all of that information. And by doing it this way, we are also significantly reducing the functional coupling. Because if we decide that from now on, all of those costs incurred, we're only going to charge them at the end of the year, well, then we remove that subscription. But that summary event that we're publishing at the end, it's unaffected by this. Your consumers wouldn't even know the difference. And they will ensure that they always keep charging the right amount of money on that account. In my view, those more granular events remain private within the service boundary. So I can have subscribers for them as long as they are part of the same bounded context, or service boundary. I use those terms interchangeably. But then, what is a public event is that card period closed. Again, this helps reduce that functional coupling, not only in terms of which are the granular events that feed into this summary event, but also from the perspective of a period, which is a whole other concept that otherwise would leak into our consumer code. Does that make sense? Okay. So this gives also, from our consumer perspective, a lot less traffic, many less events that they have to consume, many less code that they have to write, and ultimately, many less things that can go wrong, right? So what do we achieve by thinking about our events in this public and private way and thinking about what is super granular and what would be more summarized? Because most importantly, it allows us to better control that radius of change, because we will still have changes, right? But as we saw with that example of those costs incurred, we're going to do that on a yearly basis, it doesn't affect that public event anymore. And that's very helpful because we control the consumers of those private events because they're part of our own service boundaries, so they're probably owned by our own team. And when it comes to the publicly exposed events, we can limit the amount of information that we share. I always tend to say, think about what you put in a public event that you emit and that anyone can subscribe to, and compare it to posting a drunk picture on Facebook or whatever social media you care about. You can't really change that easily because you may not even be aware of your consumers. So you have to be really private about that type of information. Just send it to your partner and move on. Right? This also helps facilitate versioning over time, and that starts by protecting our service boundaries. But we haven't solved the entire problem because we still have all of those in-flight messages that we talked about, right? Whether they're private or public events at this point doesn't even matter. Because we have in-flight messages, we would like to go to this new version. How are we going to deal with that? How are we going to deal with messages that are stuck in error queues, messages that are delayed, and all of those things? Well, the thing is that I think we should rethink the way that our systems change over time. Because change is not a point-in-time event. It is something that happens over a period of time. It's something that requires facilitation and coordination. It means that we need to think about versioning strategies and upgrade strategies. And I would like to start covering versioning strategies first. However, before we can do that, we need to take a couple of steps back and also consider how our events travel over the wire. Because when a producer emits an event, well, that event first will be serialized. It will be encoded in a specific encoding format. That can be JSON. Who's using JSON? Avro? Protobuf? XML? I mean, there's plenty, even of other options, right? It doesn't really matter. What matters is that there's an agreement between the producer and the consumer on what that encoding format is going to be. However, most teams agree on this, but then leave the content of the event completely open to interpretation. I'm emitting these fields. Well, okay. It contains an amount. What type of precision does that thing have? That can be impacted by your encoding format. Or maybe you're emitting something like a temperature. Oh, okay. Is that in Celsius? Is it in Fahrenheit? Or is it the temperature of the light, and is it in Kelvin? We don't know. We just assume that the consumer will figure it out, right? Are there any fields that are required? That's another reason that consuming code could fail, right? But we can also provide that structure by including a schema. So now we don't only have a data payload that could contain certain fields, but we have a schema that structures how exactly that would look like. This basically gives our events much more structured so that at the producer side we have a better overview of what has to go into them. But also on the consuming side, we are basically adding additional metadata that is conveying how we expect consumers to then basically interpret and deal with that information. We can provide additional metadata on complex structures. We can add information like what is required, what would be a default value, additional documentation even, that would provide our consumers with a much better ability to understand what that data really contains and what it is supposed to convey. And when we have schemas, then that also starts to facilitate versioning significantly. And then we can start talking about versioning strategies. Now, a versioning strategy is, again, something that you want to decide upon at the beginning. It's almost like a policy decision at that point. And it's basically going to communicate to everyone in the team, and even outside of your teams, how your schemas are going to evolve over time. What type of changes can I make as a producer? What type of changes can my consumers expect? So let's take a look at a couple, starting with forward compatibility. Now, in a forward compatibility mode, the schema allows for deleting of optional fields, and it allows you to add fields. Whether they're required or not doesn't even matter. You can add any of them. And this is usually very useful when you use more traditional brokers like Azure ServiceBus, okay, RabbitMQ, SQS. Okay, cool. Now, in this case, our consumers can use the previous version of the schema. So I could be on V1, and I can still consume events that were emitted based on V2 of the schema. And in this type of a scenario, our producers are going to upgrade to the newer version of the schema first. And this is not always easy to comprehend, so I also have an example. Let's say we begin with V1 of the schema, and both our producer and our consumer are using this version of the schema. Everything is good in the world, right? But then we introduce V2. And as I said, our producers are the ones who are going to move to this new version of the schema first. Now, what we've done is we've removed currency. That was an optional field to begin with, right? So if I'm a consumer using V1 of the schema, I can still deal with this event that was emitted with V2 of the schema because it will just not have a currency, and I was already prepared to deal with that. When the consumer is ready, can upgrade to that newer version of the schema. Another change, V3 comes along, and at this point, a new required field is added, the balance. Again, our producer is going to upgrade first. You could say, well, how does this work? Well, as a consumer, using V2, I will just look at that payload and ignore balance. I don't know what it is anyway, so I can deal with that, still consume those messages. And when I'm ready, I can then also upgrade to that newer version of the schema and start using this new attribute that was introduced in the payload. But let's look at this also from an infrastructure perspective, okay? So as a publisher, I'm publishing an event of a certain type onto a specific topic. And as long as the changes that I make to the schema are forward compatible, then I could publish V1 and then start publishing V2. And all of my consumers that expect V1 of the schema will still be able to deal with events that were emitted with a next version of that schema. So nothing needs to immediately change for those consumers to be able to continue. We can basically upgrade without breaking half of the system. Now, another option is to use backward compatibility. And that allows you to delete fields, and it allows you to add optional fields. Now, this is a little bit of the reverse. And in this case, consumers can use the next version of the schema to still be able to consume messages that were constructed with a previous version of the schema. This can be popular with things like Kafka, or if you're using event stores and saving the events as they come in. As long as the schema is backward compatible, you can still consume them, or replay, or something like that. So let's look at this again in an example. Oh, sorry, I forgot to say, in this specific scenario, it's the consumer who will start using a newer version of the schema before the producer does. If we look at this, again, in an example, V1, everything's good in the world, producer uses it, consumer uses it. And then our V2 of the schema is introduced. But now, who will start using this new version first is our consumer, not the producer. What has happened here is that an optional field, currency, was added. In Avro, all the fields are required by default, so you basically have to add this type sort of concatenation of null and string and then set the default to null. But again, if as I can still basically using V2 of the schema, I can still deal with all of those messages that are being produced under V1 of the schema because I just added an optional field. It's not going to be there. It's fine. I'm prepared to do that. So then when the producer upgrades to that new version of the schema, a new one could be introduced. And what happens at this point is that we have removed this period 2 field. Now, at that point, again, it's the consumer who is going to upgrade first. And we can still deal with any messages constructed under V2 of the schema. And then when all of the consumers are upgraded, then the producer will also upgrade. If we look at this, again, from the infrastructure perspective, it's a little bit different. Because what we have here is our publisher keeps sending out V1 of the schema. But some of our consumers have upgraded to that V2 of the schema and are still perfectly able, with that schema, to deal with those messages from V1. Does that make sense? All right. But there's also full compatibility. Now, you can guess it, right? This allows you to delete only optional fields and add only optional fields. So much more restrictive. Now, in this case, consumers can use an old version of the schema or a new version of the schema to deal with messages that were processed either with an old or a new. So the best way for me to explain that is that if I'm a consumer and I'm on V2, then I can process messages that were emitted with V1 of that schema or with V3 of that schema. Now, this is the most restrictive mode, but you could even restrict that further. And that's with transitive compatibility. Now, transitive compatibility is not a versioning strategy unto itself. It's rather an attribute that you would apply to any of the compatibility modes that we just discussed. So backward, forward, or full compatibility can also be transitive on top of that. So what does that really mean? It means that when we talked about all of these different versions, I went version 1, then we go to version 2, wait until everyone is upgraded, then we go to version 3. Because that compatibility is only guaranteed across the previous version or across the next version, depending on the compatibility mode, right? But when we make it transitive, we are basically saying this compatibility applies to all of the versions of the schema. Now, this can be very useful if you have very long-lived events or if you have them stored somewhere in an event store, data lake, whatever it is, right? Or even if you have very quickly evolving systems and your consumers are not catching up quickly enough, then it can also be very interesting to use something like this. Now, I also want to point out a misconception that tends to happen regularly when I talk about compatibility and even transitive compatibility, whatever is in schema versioning. And it's a trap that I have fallen into as well. And that's the idea that schema versioning is not the same thing as semantic versioning. Who uses SEMver, semantic versioning? Okay. Most hands, half the room, I would say. So semantic versioning is a way to version your public APIs. However, schema versioning is something that behaves very, very differently. But people confuse these things all the time. Why? Because we express our schemas in APIs. We express them in code, right? We have some, customer object or whatever it is, and that has its schema, but we also express that in our code in an object, whether it's a Poco or a Pojo or whatever it is, doesn't matter, right? And the thing is that when you look at it from the code perspective, deleting a property would be a breaking change because the calling code would literally stop compiling. But that's semantic versioning. It would be a breaking change. But from a schema versioning perspective, it's not necessarily a breaking change, depending on your compatibility. So it's really important to separate those things from each other and to not have your contracts, therefore, live in the same code that you're going to version semantically, because those things don't evolve the same way. So it's important to remind yourselves that schema compatibility is only about the ability to read the data that's coming in. I want to be able to deserialize what is coming in without blowing up. I want to be able to understand that data and know what to do with it and know how it's structured and know how I am supposed to interpret all of that information. It is not about public surface APIs. They are not really. But it becomes difficult because sometimes we put them into shared packages. Anyone does that? Shared packages for their data contracts? Okay, and who copies them across producer and consumer? Okay, and who sends the schema over the wire? Okay, wait, who uses a schema? Okay, just checking. Now, the goal here is to avoid those poison messages. We want to avoid our consumer code from breaking when we start to produce something that is new, that has had to evolve over time. But actually, the payload of an event that we emit is not the only thing that can change. So we have a data structure that we send over the wire. That's not the only thing that could break a consumer. What else could break a consumer? Sorry? Headers, exactly. Metadata. This is often forgotten about. But again, what we put into our event structure is not everything that travels on the wire because we add metadata, we add headers. And those headers can also start to break our entire pipelines, our consumers, because those headers are often used by intermediate parties for routing purposes, or they could even be used by consumer code. I don't know, to get additional context for processing, for example. So it becomes really important that we also start thinking about that part. How do we deal with metadata changes? And that's where cloud events come in. Who's heard of that before? Okay, who uses it? Couple of hands. So cloud events is actually a specification that was built by the CNCF for event metadata. They also have plenty of implementations of this across multiple languages and SDKs that facilitate the usage of cloud events, and it's been adopted in many, many different brokers already out there and other tooling as well. But what it really aims to do is it aims to standardize the envelope, the metadata, the headers that travel on that wire. And they basically introduce 7 attributes that the specification already knows. So 4 of them are required. The ID, what is a message ID? What is the type of this message? What's the specification version? So it knows what to do with that, but there's only one. And it's probably going to stay like that for a very long time. And then there's also the source. Where did this message come from? Those are the 4 required headers that you would always have to include. And then at least they have the same name everywhere. And you can expect them to be there in a sort of standardized way. Now, this is also protocol agnostic, but it supports multiple protocols because it has bindings for HTTP and AMQP and MQTT and Kafka and NATS, and you could even contribute your own if you want. Now, what I really like about cloud events is that it will allow you, with its extensible model, to also register your own extensions or your own headers. Because who uses custom headers in their systems? Okay, probably like half of the room. And it can be a very good way to convey additional information that you don't want to put into your payload. And with cloud events, you can start to structure those as well. It doesn't have to be limited to the event schema alone. So you have this ability to structure those as well. But sometimes the changes that we have to make in our systems are really impactful, and we try. We try to take care of that event structure, and we have a versioning strategy, and we have our event metadata that's structured with cloud events. But then the time arrives, and we really, 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 really need a breaking change. And the first thing I would tell you is try to figure out why you don't really need a breaking change. And if you really, really can't, okay, then you need a breaking change. It happens. What now? What do we do? Well, first, we need to deprecate this old version that we don't want to support for the rest of our system lifecycle anymore, and we want to set a removal date. We're going to keep this around for a while, but by this date, we are going to remove it. Then you notify your consumers. And then, within that deprecation window, you want to do what's called dual publishing. You want to publish the old version of the event for the consumers that haven't updated yet, and you want to publish this new version of the event so that the ones that are keeping up more quickly can start to upgrade to that new version. And then you stop publishing the old version of that event after the deprecation window is gone. If you don't keep to that date, you're losing your autonomy. This is your autonomy. You can make changes that are even breaking. You don't just impose them on consumers, you give them a little bit of time to adjust, and then at some point you remove them. Now, to basically deal with these types of changes, we need an upgrade strategy. We are beyond versioning strategies at this point. And it's impossible to go over all of the possible options because which upgrade strategy you end up with is going to depend on what type of broker do you use. What type of compatibility have you chosen? And all of those different concerns are going to feed into that. But I would like to at least give you an idea. So I want to talk about a scenario in which you would be using a message, a message broker, like let's say Azure ServiceBus, and you're using forward compatibility. So basically your messages are very short-lived. Once you consume them, you delete them, okay? Now, in the start situation, everything is good in the world. We have a publisher that is publishing an event onto a topic, and we have a sub-queue or a virtual queue per subscriber that is then receiving all of those messages. Everything is good. But at some point, the publisher is like, no, we have a breaking change. It's important that I called those VA and VB, and not V1 and V2. Why is that? Sorry? Well, we don't talk about semantic versioning when it comes to schema versioning. But the thing is that the semantics of the message have changed. They don't necessarily even mean the same thing anymore. We have done a breaking change. Our consumers are going to have to go into their code and change that in order to be able to deal with this new thing. And because of that, it's a different type of event. And because of that, in this scenario, we've chosen to have a topic per event type, so it becomes a new topic. Yes? OK. We start doing that dual publishing. And at some point, we have a subscriber that wants to upgrade. Now, that subscriber, number one, needs to subscribe to this new event type, VB, and unsubscribe to from this old event type, VA. Now, when we do that, then we get an additional sub-queue that contains these new messages. We don't necessarily lose that old sub-queue just by unsubscribing. So we have saved all of those in-flight messages, and we can continue consuming them until that sub-queue is empty. What is really important here is the order of these operations. Subscribe to the new event type first, unsubscribe from the old event type later. Of course, you want to do these operations as closely together as humanly or physically possible. But we know that these are not atomic operations, right? So there could be milliseconds, seconds, or even a longer period of time if something goes wrong in between those operations. If you would unsubscribe from VA first and subscribe to VB later, what does that lead to? Message loss, exactly. So turn it around. But if you turn it around, what could you then end up with? Duplicates. So what do you want to do? Deduplicate based on a logical message ID. So you need to have thought about that as well. so that you can understand that on the consuming end. Okay, then once we got rid of all of those in-flight messages, that subqueue can be deleted, and we can also get rid of the handler that deals with that previous type of message. And once, hopefully, all of our subscribers have upgraded, and otherwise, at this point, it's their fault, okay? Because you've given them a deprecation window. Don't set that to a week, okay? Give them time. But you've set the deprecation window, and when that time arrives, you're going to stop publishing that VA message. You can remove the necessary infrastructure surrounding it as well. And this closes the circle on schema versioning and upgrading to completely new versions as well. But at this point, the only thing that we've done is we've made promises, right? I promise as a producer that this is the compatibility strategy that I'm going to follow. Cross my heart, hope to die. And even if we pay a lot of attention to this, sometimes these things happen by mistake. So it's nothing but a promise because none of this is enforced. And when we make mistakes here, this can cause massive issues in all of our consumers, all of those downstream services. Now, I really like this quote from Clemens Wassers, who was in his talk yesterday. Okay. So he basically said that distributed systems are hard enough when we keep our promises. It's okay, no worries. They become absolute chaos when breaking those promises is easy. So how do we ensure that we enforce our promises, that we're not just, making empty ones? Well, for starters, we use a schema registry. And a schema registry basically brings a centralized approach to that schema evolution. It's accessible to both our producers and our consumers. They can query that information, they can use that information. And once we use a schema registry, we don't necessarily have to include the schema as part of the payload for those of you who are doing that. You could just have maybe the name of the schema or even a URL, and that's it. You have access from both the producer and the consumer side. This basically takes a compatibility promise and formalizes it into something that can't easily be broken. And finally, it also allows you to query that schema on the producer side and enforce it on egress or whenever you publish an event or a message. And this basically then gives you runtime validation of payloads at that point, right? It avoids those poison messages. But there's a problem with schema registries. And that's that they're very tightly coupled currently to protocols and to brokers. Who's using schema registries? Okay, keep your hand up if you're using Kafka or Azure Event Hubs. Yeah. So the thing is that if you're using a more traditional message broker like Azure ServiceBus or SQS or RabbitMQ, I don't see schema registries being used in that space because they're so tightly coupled. Like even if you would look at Azure, you would need to have an Event Hubs instance in order to use a schema registry because it's a feature of that service, which you're not going to pay for if what you're using is Azure Service Bus. Doesn't make any sense. But that's about to change. And for those of you who are in Clemens' talk, you will recognize this. Now, I want to introduce X Registry, which basically provides a set of specifications that are going to help us with this a little bit. Well, actually, not a little bit, hopefully a lot. Now, this was recently developed under the CNCF by the same group that also developed cloud events, and it's currently a sandbox project in CNCF. And this can be used to define any type of meaningful information as long as it adheres to that standard structure that we'll look at in a minute. It's not necessarily tied to messaging, but it's very convenient for messaging, and that's what we care about, so that's what we're going to look at. Because in the context of messaging, there are also deriving specifications that will help us categorize endpoints, messages, and schemas. So what that does is it basically brings a foundation for centralized registries, not just for schemas, but also for endpoints and our message definitions. It's protocol and broker and vendor agnostic. So it's going to become much easier to have this across the line, whichever broker you're using, in your entire system if you're using multiple types of brokers. And that registry can again be used both for discovery and for validation. This gives you a lot of visibility as well into the events that a producer emits, because you can look at an endpoint and see what comes out of this thing. How do we usually do that? With documentation that's never kept up to date, right? Now, the cool thing about this is that this specification could be supported by the existing schema registries. It's not supposed to replace any of those things, right? It's basically extending those capabilities much further out so we can get value from that idea across the board. So the way that this looks like at its core level is that you have a registry. There are groups in there, and each group has multiple resources that are of a specific type, and each resource can have multiple versions. If we translate that into messaging world, which is what we care about, then one of those groups is an endpoint. So basically, an endpoint is a group type. An endpoint, that then includes things like the channel and the protocol, even the envelope that's used. Is this using a cloud events envelope or not? And that then can contain multiple message definitions. What is a message definition? A name. Where does this come from? What are the headers, right? That has a single version currently, as it's currently designed. But this is a specific choice from the cloud events specification derived from its registry. What we also have on the other side is that we have, as a group type, schema groups. So we can also have our schemas in there. And then, as a resource type, that would be a schema, part of a group. Allows us to put stuff together that is meant to be kept together, and also access control and things like that. And then a schema can have multiple versions. But what is also really nice is that it allows cross-linking. So now I can go into an endpoint, look at one of those message definitions, which, remember, only contains headers, and say, well, the payload of this thing needs to have this schema. And then basically you connected everything. And that defines the structure of your metadata, of your message body, and you know which endpoint it's coming from. So you have the entire story. But how is this useful for versioning? Well, basically it gives you a single point of truth for the entire story, for the endpoint, for the message definition, for the schema that it's using. It also defines compatibility in its core specification, which is something that I proudly contributed to this specification as well. So the compatibility modes that we talked about, they're well known in schema registries, and the X registry specification supports that, but in its core specification. So for anything that you would like to use. It also can be used the same way on egress to avoid all of those poison messages, which is great because it applies to both the schema and all of that metadata. So you can't break anything anymore if you're using this correctly. And finally, it also facilitates that deprecation through its evolution model. Remember when I told you that when you have a breaking change to your event, you need to notify your consumers? I just sort of glanced over that, danced around it. Because how do you do that? How do you even know who your consumers are? What if they are outside of your own system boundaries? Well, that's another thing that X registry facilitates, because it will basically emit cloud events whenever one message definition is deprecated. A cloud event will be emitted and will say, I'm deprecated. I'm around until this date, and after that, I'm gone. I am replaced by this new message, which you can go find in the registry. And this allows you to keep your producers completely decoupled from your consumers. You don't have to be aware of them, which is how it was intended to begin with. This is something that's currently being worked on, so you will see that appear in time. Now, this specification is currently RC1. If you want to go take a look at it, would be very welcome to get some additional feedback, and then we'll hopefully start to see adoption out there that can help us work with this. Now, there are already implementations of this running, and reference implementation is already available. You can run this in a file, okay, next to your code base and use that. Or you could use an actual server. You could host that on Blob if you want. So there are a lot of options with this. And that brings me to the end just in time. Now, to conclude, facilitating versioning an event-driven system, that really starts with well-designed events. It's something that we need to keep in mind from the beginning. How are we going to design these events so they don't break? What is also our versioning strategy? This is a policy decision. It is a decision made at the beginning that is not easily changed after, because it has very hard dependencies. Your event metadata shouldn't be forgotten either. You have headers that your consumers can rely on, that your intermediates rely on. So make sure that you also define those using cloud events. And enforce your promises, right? You can use a schema registry, and who knows what other types of registries we'll see once X registry also is live. And finally, it's important that you have a breaking changes strategy that you have in place so that you can notify your consumers early on. Let's let everyone take a picture. But don't worry, as always, I have resources available for you to do some additional reading, to find additional information. I'm happy to hear any questions you have. I'll be around for the rest of the conference. Thank you very much for joining me here.